So recently I've been working on trying to find new promising hydrogen storage materials. So we compress simple molecules together, like hydrogen plus water, hydrogen plus methane, and then we found some very interesting new phases that store a lot of molecular hydrogen. So it holds some promise for hydrogen, for the hydrogen economy. In terms of realizing a hydrogen economy, that would involve both first producing the hydrogen, then storing the hydrogen, and then using the hydrogen. So in all three of these steps, there are some obstacles. And there's issues with kinetics and thermodynamics, so you may have to put in a lot of, so for example, for metal hydrides, which is a very commonly studied area of solid state hydrogen storage, you get out a lot of energy when you react the metal plus hydrogen to form the metal hydride. But then you need to put in pretty high temperatures to then get the hydrogen back out. So that's a problem. Like the temperatures are a little bit higher than you'd want to have in your car, like a few hundred degrees for the storage. So it binds the hydrogen almost too well. And then you have so on that side, so you have almost a Goldilocks problem where you have some materials that bind hydrogen too tightly. So if you want to recharge the material, you need to, you first gives off a lot of energy when you form the metal hydride, so you need to manage the temperature, thermal management there. Also, when you desorb the hydrogen, you need to put in heat to get the hydrogen out. So it binds hydrogen, well the net effect is it binds hydrogen too tightly. On the other side, you also have ways that people are thinking, well, why don't we have some weaker interactions? So just have the molecular hydrogen physically absorbed. So it can be trapped in like framework structures, like carbon nanotubes. But here then, the hydrogen isn't bonded strongly enough, so you need low temperature, or you need some pressure. So it's really hard to find the right middle zone where you have just the right interactions, where the hydrogen is bonded strongly enough that it doesn't give off, you don't need to put too much heat to release it, but also you don't need to cool it in order to store it in the hydrogen. And so, to store the hydrogen. So it's a matter of finding the right materials at the right conditions. So right now, for the cars that are actually people have prototypes for, it's usually compressed gas. And that's because it's very simple to think of how you would just have a tank that can withstand pretty high pressures, and you can just pump the gas into the tank. So I think technologically wise, it's pretty straightforward. Liquid hydrogen also has, there's research into that, but you need very, very low temperatures to liquefy hydrogen, 20 Kelvin, so really, really low temperatures. And then you can imagine that once you need to keep the car at that low temperature, because if you park your car and you wait a couple days, you wouldn't want the hydrogen to start boiling off and then creating high pressure hydrogen gas in a tank. So I think compressed gas is just easiest to use, but it has the lowest hydrogen density. Then liquid hydrogen, you're doing a little better. You have higher hydrogen density, but there's some issues with boil off, and also the hydrogen density isn't as high as you'd want. So then ultimately, I think if you really want to have some practical hydrogen storage material that would have any chance of being even close to competing with automobiles, it'd have to be solid state storage, because solid is the highest energy packing density. So we're definitely in the stage of fundamental basic research. All my research is understanding materials at high pressure, and at high pressure, pressure is a good way of tuning materials' properties, and so you can produce new phases, novel bonding and interactions. And so it's feasible at high pressure you could discover some very promising hydrogen storage material. And so that's what we're opening up the field for exploration to both pressure, temperature, and composition, looking for promising new phases. And then once we find a promising phase, then we can think about how to make it more practical, using pressure to discover new materials. That's just kind of a very new idea. And in every system we've looked at so far, we've found like 3 or 4 new phases. So it's definitely an area which everything we've studied, we found interesting things in simple systems, so simple binary systems. You can imagine if you start looking at ternary systems, you find even more things. So it's just really something where we've only barely scratched the tip of the iceberg.